Welcome to Math 201, Lesson 4.3, Part 2. Today's lesson begins with an activity, parks and optimization. So pause this video, work through the problems that follow, and then press play when you're ready to go over them. A park ranger, you know that the price of admission affects the number of people who enter the park each day. So right now, the price is $4 and 200 people visit each day. After some careful study, a consulting firm says that for each 25-cent increase in admission price, 10 fewer people will visit the park. You and your fellow park rangers decide you should maximize your daily revenue for the long-term health of the park. So we're going to let X represent the number of times you increase the admission price by 25 cents and write a function for the number of people who enter the park in terms of X. So right now, we have 200 people entering the park. Um, and we are going to do 10 fewer people every time we increase the price. So for every price increase of 25 cents, 10 fewer people enter the park. So we're going to do minus 10 people every time we increase the price. And X is representing the number of times we increase the price. So the number of people who enter the park is going to be 200 and then minus 10 people every time we increase the price. So here's our formula for the number of people who enter the park, 200 minus 10x. Using your function from A, write a function for the total revenue of the park. Hint, how much will each person entering the park pay? So in general, revenue for anything kind of is equal to the number of visitors or the number of customers times the price each customer pays, the price each visitor pays. Okay, so you have the number of people who come to the park times the price that they pay. That's the total amount of money that comes into the park. That's called revenue. Okay, so the number of visitors to the park, we just wrote a formula for that. That's 200 minus 10x. And then the price that each of them is going to pay depends on X, the number of times we've increased the price, right? So right now it's $4 and it's going to go up 25 cents. Each price increase is 25 cents. So I'm going to do plus 0.25X plus 25 cents every time we increase the price. And X is the number of price increases. So this is the price that each person pays. It depends on X, how many times we've increased the price. So if I multiply these together, I get revenue is 800 plus 10x minus 2.5x squared. I just did a quick FOIL, combined my like terms, and I end up with this formula for revenue. What admission price will maximize the daily income of the park? So we start by finding critical points. So let's write down our revenue formula again. It was 800 plus 10x minus 2.5x squared. Okay, so the way we find maximums and minimums, we start by finding critical points. Okay, so critical points happen when the derivative is 0. So I'm going to take the derivative r prime, and I get 10 minus 5x. So critical points happen when the derivative is 0 or the derivative is undefined. This derivative is never undefined, but I can set it equal to 0 and solve it. And we get x equals 2. So there's our critical point. I just need to make sure that this critical point is in fact a maximum. We want to maximize revenue and make sure we're not minimizing revenue. So I'm just going to make a number line. I'm going to put my critical point on it, and I'm going to look at the sign of r prime. Okay, if I plug in a value smaller than 2 into r prime, like 1, okay, I'm going to plug a 1 into r prime. So I have 10 minus 5 times 1, which is 5, which is a positive number. And if I plug something bigger than 2 into r prime, like 5 or 10 or 100, I'm going to get a negative number. So put a negative there. And that tells me that r goes from increasing to decreasing. So we have a maximum, right? X equals 2 is the location of a maximum. So to summarize, two price increases of 25 cents yields um, an entrance fee of $4.50, right? Because it was $4. We did two price increases of 25 cents um, to maximize revenue. Okay, we now have another activity, widget boxes. I'm going to have you pause the video, work through these problems, and then go ahead and press play when you're ready to see me go over them. Maria is constructing boxes out of sheet metal for her hardware store to display widgets. Each box has two compartments with equal dimensions, each holding 72 cubic inches. Okay, so each compartment in this box holds 72 cubic inches. Equal dimensions, which means this distance equals this distance. We've labeled this a 12. Okay. Marissa wants to minimize the amount of material used to create these boxes. Each box has a base and four sides, plus a common vertical interior divider made of the same material. There's no lid on the box, and her shelves have a horizontal depth of 12 inches, so that dimension is fixed. The two other dimensions can vary, so that being this front across dimension and this up dimension. So here's the box. We want to label the diagram with variables L and H representing the unknown lengths. Okay, so let's call this distance L across the front, and we'll call the height H. Now, number two, we want to write an equation for the total amount of metal used to construct the box in terms of L and H. So the total amount of metal we use is the surface area of the box. Okay, so we're going to say the area used is made up of several different pieces. Okay, so I have this front piece and this back piece that are the same. And each of those has an area of L times H. Okay, so it's the front piece and the back piece. I have two of those, two pieces that have area LH. Okay, and then I have the two side, actually I have three pieces, the two side pieces and the middle piece that all have the same dimensions. They are H by 12. Okay, so I have three pieces that are all 12H for their area. And then I have the bottom piece. So the bottom piece is L by 12. So to simplify, I have 2LH plus 36H plus 12L. And now I'm supposed to write a volume equation in terms of the same variables. So the volume of the box is 12 times L times H. The volume of a box in general is length times width times height. So it's going to be 12 times L times H. And they told us that the volume of the box is supposed to be 144. They actually said that each compartment of the box is 72, but that means altogether the volume is 144. 12LH. In number four, I'm supposed to identify, I have two equations. I've got the area equation that I wrote earlier. Bring this down. There's my area equation and my volume equation. And it says one of these represents a constraint and one is supposed to be optimized. Okay, so they asked me to minimize the amount of material I use. That is the area equation. So I want to minimize area. And my other equation, my volume, is the constraint. Okay, number five, we want to write the equation we need to optimize in terms of one variable only and specify the domain. Okay, so my equation that I want to optimize is 2LH plus 36H plus 12L. And it right now it has two variables in it. I want one variable only. I use the constraint equation to solve for one of my variables. So this 144 equals 12LH. I'm going to solve it for L. Okay, if I want to get L by itself, I'm going to divide both sides by 12H, and I get 12 over H. And then I can go to my area equation, and everywhere I see an L, I'm going to replace it with a 12 over H. So I have area equals 2 times 12 over H times H plus 36H plus 12 times 12 over H. And then I can just simplify a little bit, and I get area is those H's cancel. And so I have 24 plus 36H plus 144H to the negative 1. And then let's think about the domain. The domain for H being the height of the box. The smallest the height of the box can be is 0, and they didn't give any other constraint, so it could go up to infinity. Finally, I want to find the box dimensions which allow Maria to use the minimum amount of sheet metal. So I'm just going to rewrite my area equation here. The function I'm trying to minimize, which was 24 plus 36H plus 144H to the negative 1, domain 0 to infinity. Okay, to maximize or minimize, to optimize a function, we start by taking the derivative and we find critical points. Critical points by taking the derivative, setting it equal to 0, or finding out where it's undefined. So my derivative of this function would be 36 minus 144H to the negative 2. And I want to set that equal to 0. This is undefined when H is 0, but 0 is not part of our domain, so I don't have to worry about the place where it's undefined. To solve this equation, I get 36 equals 144 over H squared, which means that I can multiply both sides by H squared, and then divide both sides by 36, and I get H squared equals 4. Which means H is plus or minus 2, but ignore the negative 2. It's not part of the domain. So now I just use a sign chart to determine whether 2 is a maximum or a minimum. So here's my sign chart. I'm putting 2 on it with a little fence, and I want to look at A prime, which is 36 minus 144 over H squared. Plug in something smaller than 2, something bigger than 2. I gotta make sure I don't go smaller than 0 because my domain is 0 to infinity. But I'm gonna plug in maybe a 1. If I put a 1 in here for H, I get 36 minus 144, which is negative. And then if I plug in something bigger than 2, like 10, right, I get 36 minus 144 over 100, which is a positive number. So now that I know the signs of A prime, I can think about A. When it's negative, it's decreasing. When it's positive, it's increasing, which means that 2 is a min. Okay. So the dimensions of the box that minimize surface area are, well, we know H equals 2. That's what we just discovered. Like H was our variable here, and it equaled 2. And then L we can calculate because L was 12 over H. We can go back a slide. L was equal to 12 over H. So that's 12 over 2, which is 6. And these were all in inches. Okay. And then the depth, which was given and never changes, was 12 inches. So height of 2 inches, length of 6 inches, depth of 12 inches. That will minimize the surface area and thus the amount of material used to build the box.